Welcome to Spring LIB.
This is chapter 37, problem number 38. We have two protons undergoing a collision. So let's say the velocities are v for both, and the masses are capital M. We know the rest mass of protons are given to us. So after the collision, actually, so let's say this is before, and after the collision, we have both protons at rest, both protons, and a new particle is now generated by this collision, and they're all at rest after the collision. And we are asked to calculate the initial speed of protons. So we're asked to calculate v in part A. So actually, we can solve this problem easily using the conservation of energy, right? So initially, like total energy that we have in the system initially has to be equal to the total energy of the system after the collision. So let's say initial and final to refer to before and after collision. Initially, let's look at what we have. We have two protons. They're moving with a certain speed, which means that we're going to have kinetic energy of the first proton plus the kinetic energy of the second proton plus the rest mass, the energy. Let's call this E naught 1 to refer to the rest energy of the first proton and the rest energy of the second proton. That's all we have before the collision. So this is the total energy of the system initially. After the collision, we have three particles now. Both of them are protons and the other one is a new particle. And they're all at rest. So no kinetic energy term on the right-hand side. All we need to have is E naught 1 again, the rest energy of the first proton, the rest energy of the second proton, plus the rest energy of this new particle, okay? So as you can see from this equation, we know the rest mass for a proton would be m times c squared, but we don't have to calculate it because we have the same terms on both sides. They can cancel out. Now we have twice the kinetic energy of the protons equals to the rest energy of a mu particle. So let's write what kinetic energies would be. So the kinetic energy of the first proton equals kinetic energy of the second proton, since it's given to us that they're moving with the same speed initially. So we call this Ke, and relativistically speaking, this equals to gamma factor minus 1 times mc squared, right? So this is what we have on the left-hand side, twice of this term here. So we can put it there, twice gamma minus 1 mc squared. This capital M here is the mass of proton, obviously. And on the right-hand side, we have the rest mass for, let's, instead of mu, let's just put nu there to refer to the rest mass of this new particle times c squared, right? So we're going to solve this equation for gamma factor because it has the information regarding the speed in it. Now, c squareds are going to cancel each other out. Let me continue this. Well, 2 gamma factor minus 1 is going to be equal to m of the new particle divided by the mass of a proton. So if we divide both sides by 2, these are going to cancel out. Gamma minus 1 is going to be equal to m nu over 2m. So let's add 1 to both sides to isolate gamma. On the next page, gamma then is going to be equal to m nu over 2m of the proton plus 1. Now, we know that the gamma looks like this. Gamma equals 1 over square root of 1 minus v squared over c squared. Since we're looking for V, which is in denominator, then from this equation, if I take the inverse of both sides, then what I'm getting is basically 1 minus V squared over C squared, correct? Then if I take the square of both sides of this equation, then what I have is 1 minus V squared over C squared equals to M nu over 2 capital M plus 1. We had taken the inverse of it, and now we're squaring it, so it's going to be square of the inverse. The order does not matter. And again, we're trying to isolate V out of this equation. In order to do that, we can take this term on the right-hand side to left and this term that contains V to the right-hand side. 1 minus M nu over 2M plus 1. The square of the inverse is going to be equal to V squared over C squared. So now we're going to multiply both sides by C squared and take the square root. Ooh, this was some algebra. From here, then V equals, we can take C out of here, right? And write it at the end. Square root of 1 minus mass of the new particle over 2m plus 1, but only square of the inverse of this term. So let's use a different kind of bracket here. Times C. Again, C is out of the square root. Now if you plug everything in there for m nu, you plug 9.75 times 10 to the power negative 28 kilograms. And for capital M, rest mass of a proton, we're going to have 1.67 times 10 to the power negative 27 kilograms. And plug everything back in this equation, you're going to see that the speed is going to be equal to 0.633 times the speed of light in this case. So this is the speed of each proton initially before the collision, right? Now, in part B, we are asked to calculate the kinetic energy of each proton. Now that we know the speeds are 0.633 times c, it shouldn't be that hard, right? The kinetic energy of the first proton equals the kinetic energy of the second proton, and we call it Ke in the first part. It was gamma minus 1 mc squared. Now let's plug in for gamma 1 over square root of 1 minus. Now we know the velocity. I can just plug it in there. Square root of my speed over c squared minus 1 times m 1.67 times 10 to the power and negative 27 kilograms times 3 times 10 to the power 8 meters per second squared. So if I do the algebra, I find something like 4.385 times 10 to the power negative 11 joules. But in the problem, it's specified that we write the answer in terms of mega electron volts. So in order to get there, first we need to do a couple of conversions. 1 EV would be equal to 1.602 times 10 to the power negative 19 joules. And also 1 mega electron volt is 10 to the power of 6 electron volts. When we apply the conversions, which means we're going to divide 4.385 times 10 to the power negative 11 by this number first, and then 10 to the power 6, we're going to get 274 mega electron volts as our answer to part B. which is the kinetic energy for each, again, kinetic energy for each proton. Now, in part C, we're asked to calculate the rest energy of our new particle. So the rest energy, easy, we wrote it down before. It's going to be m nu times c squared. M nu is given to us, 9.75 times 10 to the power negative 28 kilograms. And then we have the speed of light, 3 times 10 to the power 8 meters per second. Square of this is going to be equal to 87.75 times 10 to the power negative 12 joules. Again, if we do the conversion to mega electron volts, you're going to see 500. You're going to find that 548 mega electron volts. Now, in part D, we're asked to discuss the relationship between our answers to B and C. Remember what we found in B. We found the kinetic energy of a proton to be 274 mega electron volts. And now from part C, we know that the rest energy of the new particle is actually twice of it. Well, this tells you clearly something about the conservation of energy, right? The initial total kinetic energy was twice of this because you have two protons, and if you have 274 mega electron volts per proton, then for two protons, you actually have 548 mega electron volts, which is not a surprise. You know that the initial total kinetic energy is actually producing this new particle.